Everyone, and welcome to the next lesson we're going to have in the notes for chapter 3, which is going to focus on doing a number of calculations in chapter 3, some of them by hand and some of them with StatCrunch. In order to focus on what we're looking at, this is a continuation. I think it's page 3 of the notes. Before doing this, you should have watched the first video where I outline all the terminology in the 3 sections of chapter 3 that focus on the measure of center, measure of variation, and measure of position. And you'll hear me refer to the vocabulary around this as we do a number of these calculations. So without further ado, let's go ahead and take a look at this. So we're going to use StatCrunch to see how we calculate a weighted mean. Oops, sorry. Guys, someone attempted to join the meeting. I was doing this for my summer class. I don't know why they attempted to join the meeting. Anyway, this just came up. Let me go ahead back to this. Here we go. Yeah, I had was using a summer class, and one of my students, I guess, probably got notice about this and attempted to join. Here we go. So let's go ahead. We're going to do a new share. And we're going to go to StatCrunch. So what I've done for the question below is I've already put in all of the information that I have on the sheet here. They're going to be using through the activity. I already have that in StatCrunch. When you're working in my math lab, one of the tabs that you're going to have an option to do is to take the work that you have in my math lab and import it directly into StatCrunch so there's not a risk of making a mistake. So let's say, for example, there was a question, as you'll see on the first page of the worksheet there, that asks you to find the weighted mean, like average, of Oscar winners. So, and we see that we have this in a frequency distribution where we have the age of Oscar winners here for men, and then the frequency of these Oscar winners at their various ages. Now, I only put 0 for 80 to 89 here. Yeah, no one over 80 for as far as a man is concerned has ever won an Oscar. There was one woman, I believe it was Jessica Tandy, for Driving Miss Daisy, who won an Oscar. She was quite old when she won that award. But I put 0 here just to kind of be consistent with the information we have over here. Having this is not necessary, but it won't compromise the calculation either. So what we're going to do to get a weighted mean for this is we're going to follow the directions on here, and that's going to say go stat, summary stats, and we go to group or bin data. So this is all down for you, but I figured just pause here a second so you kind of see where we're going with this, because knowing these steps is going to be very helpful when you're using StatCrunch in your homework and especially a test. And now once we get to the right menued area, now we kind of have to know what we're going to pull from. Now, because you have multiple bits of information here, I want to find this for the age for the best actors, not actresses, but actor. And I'm going to do the counts in the frequency, and I have M here as opposed to frequency for female. We want to make sure this is the information that's paired with this, so we want to make sure we select that. If you're pulling a question in StatCrunch, it should limit the information that's in StatCrunch because you'll be focused on that one question only. I chose to put all the information here at once just to show you the availability of this feature, as well as to be careful when you're sorting through information up here. Now, the only thing I'm concerned about getting is the mean. However, you can get the standard deviation, you can get the number of n values, it'll figure all kinds of stuff here. But the only information for the moment I'm really interested in is the mean, and then perhaps maybe standard deviation later on. But it kind of defaults this already. So from this point, I'm going to go ahead and I'm going to click compute. And you'll see here, I have 87 people who won an Academy Award for being Best Actor. Their mean age is 44.5, which is the main thing that we're looking at. The standard deviation of their ages is 9.64, we'll say, is rounded to the nearest hundredth. So the standard deviation is going to be 9.64. We could probably just say 9.6. That's about as accurate as we need to go because age is measured by a year. And the median is also, interestingly enough, the median is also 44.5. The way this is usually done is we would find what the median of each of these is. Like this is the median of this would be 20 plus 29 is 49. Divided by 2, that would be 24.5. This would be 34.5. 44.5, 54.5, and so on. By including 80 to 89, which is not needed, the only thing that might be perhaps thrown off a little bit could be possibly the range. So I may not need to include that. Yeah, so I could probably take that out and maybe store a little bit of this, but we're not interested in that. The main thing we're looking at is finding the mean, and we have that there. So the answer for the mean for this is going to be 44.5. Okay, so you can try doing this for the actresses as well if you want to. That would be the next question, question 30 on that first page. I'm going to go ahead and I'm going to skip that again. Now if I want to find measures of center of variation position, this is going to be on page 2. Let me refer you back to that there before we go. So let's say I'm given a set of data here and I want to find the measures, like all kinds of measures of center, variance, and position. The nice thing with StatCrunch, it does all of these at once, and quite simply too. And you'll see here, these steps actually come from the book. So what I'm going to do is I'm going to show you how to do this with the data that we have on the sheet here. I typed in the data by hand, so if you find a mistake, please let me know in the comments section. I'm already seeing a mistake in this actually. What I have here, I've got 1, 2, 3, 4, maybe 4 or 500. Yeah, I didn't put everything in, so hold on. So I got to put 2 more pieces of data into this here. Okay, so I'm going to go back to the data now, and I think everything should be complete at this point. 4, 6, 8, 10. Yes, that should be all complete now. And I'm going to take this down and we'll show you how to do the calculations here. Hand. By the way, preparing the material for all this is a rather time-consuming process. And if the videos are not entirely smooth, my apologies for sometimes just catching myself in a mistake. You very well may catch me in a mistake here or there as well. Okay, so now we're going to be using this data to find all the measures of central tendency, variation, and we're going to use some of this information here for position as well. So for this, then we're going to go to stat. We're going to go to summary stats, and I'm going to click columns. Okay, and now I have 3 different columns of information here. We don't want that for this. We don't want it for this. We want it for the data that we're looking at. So we're going to make sure to put that in. Okay, what kind of information? We want to try to find everything we can here. Let's see. You notice that all these that are highlighted here are information that's already over here. You can hold the control key down and add further ones also. One bit of information I'd want is definitely the IQR, that's the interquartile range. We'll talk about that in a moment here. Also, I would probably want to find the mode. Does it do mid-range? I'm not sure. It may be here already. Let's see. Median, mean, variance. Oh, yeah, I don't think this does the mid-range, but that's okay. We'll go ahead and we'll find what the mid-range is in a second. Okay, and we're going to hit compute. And it gives lots of good information here. Definitely some information that I'm going to want to record for this data. This is a sample, so I'm going to record this as a sample mean. I'll introduce the notation for that. So I'm going to write, since we're working with whole numbers here, I'm going to round the mean to the nearest 10. Since all the data is whole number data, I'm going to round anything that needs to be rounded to the nearest 10th. So I'm going to record my mean as 365.2. I'm going to record on the variance. Let me record the standard deviation first, actually. So the standard deviation I'm going to record as 538.9. Then the variance, which is going to be s squared, and I'll show this to all you guys in a second, is going to be 290,400.39, so that'd be 0.4. The median, that's going to be equal to 200. The range And I'm putting this all on the paper here, 2461. In fact, you can just pause it if you want to, but let me go back to my paper so you guys, everyone can see what I am writing here. Okay, so the range of 2461, the minimum, that's equal to 39. The maximum, that's equal to 2500. Now, one thing that's not calculated in this is the mid-range. But this is a good time to calculate the mid-range because we have what the minimum and maximum is here. So that's going to be equal to 2500 plus 39 divided by 2. So that's going to equal 2539 divided by 2. So 2500 divided by 2 will be 1250. This is going to work out to be, I see, I want to say it's going to be 1260. 9.5, but I'm gonna just do it on my calculator just to make sure I'm doing it in my head correctly here. So 25 39 divided by 2. Hold on. 25 2. Yeah, 1269.5 it is. So the mid-range is going to be 1269.5. And you would see here that is potentially one measure of center. But where does 1269.5 fall? It falls right here, like right near the last pair of numbers. So probably not a great measure of center, but we still want to be able to find what that is. We have Q1 equaling 75. Q3 equaling 450. We have the IQR, that's going to be an important calculation for later, which is the difference of these is 40, 50 minus 75, but that gets us for us 375. And then finally, it determines that the mode is going to equal 500. Okay, so good that you record this data down because we're going to be utilizing some of this data to do other calculations that we're going to be doing in chapter 3. So what I provided here isn't meant to be kind of an exhaustive instruction on this, but it's to show at least one example of how to use StatCrunch to calculate these things, as well as to provide at least one example to complement the videos in calculating other things. So we're going to be utilizing some of the data on this page, and we'll refer back to it as needed. So we're going to give StatCrunch a little bit of a rest, and we're going to see how we calculate z-scores next here. So we're not going to use the direction for this here yet. This will be something we're going to use for later. Just remember, when it comes to z-scores, here's some important information here. Just to introduce this, when we're talking about means, there's two types of means that we're going to refer to. The distinction of these is not going to be so important at this time, but is going to become significantly more important later on. So when we talk about statistics, we most frequently work with sample data. And then we work with sample data, we'll generate something which is called a sample mean. And a sample mean is noted by what's called an X bar. Okay, so we refer to this as X bar. This is going to be a sample mean. Another type of mean, which is something we're going to look to not calculate precisely, usually, but usually we're going to work toward approximating or getting close to, is what's called another Greek letter. Now, it kind of looks like a cross between an M and a U, and it's pronounced mu. So if you're curious to know, this is pronounced mu, and this is an example of what we call a population mean. Those are the two types of means that we're going to work with. In terms of standard deviation, we have two types as well, and they both fall into these same categories between sample and population. If we're looking at a sample mean, we denote that with an S. So an S is going to be denoted by, or a sample mean is going to be denoted by S. And then if we want the population, standard deviation. population standard deviation, we denote this with a lowercase Greek letter sigma. So the capital sigma looks like kind of like a cross between an E. It looks like an E that's not without the vertical slant. It just kind of goes up top and then angle down. Like this is a uppercase E, which is used in mathematics. But this is the lowercase sigma. So that's capital sigma, lowercase sigma, and this is going to be a population. And the reason I bring up these notations now is because there are two formulas that we work with when we use z-scores. Now they're both pretty much identical to each other. So the z-score, that's going to be the measure of position, and this refers to when we treat data as being normally distributed. Not all data is normally distributed, and the distribution we're working with for this example is probably not data that is normally distributed. But in finding a z-score for it, we're going to treat it like it is normally distributed. Okay, that's just an important distinction I wanted to bring up. So we're going to get these x values. We're going to look to find the z-score for. This is going to be minus the sample mean divided by the sample standard deviation. Later, when we begin to work with data that for which we know population means and population standard deviations, or maybe just provided in the question, then it's going to be x minus mu divided by sigma. Remember, this is sample mean, sample standard deviation. This is population mean, population standard deviation. For the purposes of what we'll do most of the time, that is the formula we're going to use. So if we're going to answer a question using the data from the previous page, the data that's going to probably be helpful to know is what is the sample mean and what is the sample standard deviation. So you'll note here that we have x bar is equal to 365.2, and then we have the sample standard deviation being equal to 538.9. So let's say, for example, let's say I want to know the z-score for the value of 100. Okay, now if we take a look at 100, we should note that 100 is less than the mean value of 365.2. And since 100 is less than the mean value of 365.2, we're to expect that that z-score is going to be negative. Because anytime we have an x value that's less than the mean, it should generate a negative z-score. So for example, A, I'm going to let that random value of x be equal to 100. And what I want to do is I want to convert that to a z-score relative to the data. So we're going to go ahead and use this formula up here where z is going to equal 100 minus 365.2. And that's going to be divided by 538.9. So when I do this, I want to make sure that on top, I get this difference first. So if you're doing this on a very generic calculator, please do make sure to kind of parenthesize this before dividing by 538.9. So I would just take 100 minus 365.2. That's going to give me a value of negative 265.2. And then you can divide this by 538.9. Hang on. And we're going to just a malfunction with my calculator. All right. And what this gives me here is I'm going to write this to the nearest two decimal places. It's going to be negative 0.49. So for the value of 100 that I have here, my z-score is going to equal a value of negative 0.49. What this is saying is that this is 49 100ths 49/100th standard deviation below the mean. Now 0.49 is close to 1/2. So this would represent saying that the value of 100 is about half a standard deviation from the mean. That's what we're looking at there. Because if the standard deviation is 538, and we're looking at like negative 265, that's like this is just about half of this. So it's just half a standard deviation below the mean. We're going to take a look at another example. Let's see how we calculate the z-scores. Okay. Let's look at B. And there are other applications of this too, but we're going to be looking at other problems later on for sure. Let's say for part B, I wanted to find the z-score for a problem like 1500. So if we take a look at 1500 and we compare that to 365.2, that is not just above the mean, that's well above the mean. So we should expect that we should obtain a z-score that's going to be positive. So let's go ahead and put this into our formula now. Bearing in mind, our sample mean is 365.2. Our standard deviation is 538.9. So now for this, we're going to have 1500 minus 365.2, and then divide that by 538.9. So on top, that's going to work out to be 1134.8. That's going to be divided by 538.9. And if I round that to 2 decimal places, this is going to be 2.11. So for the value in this data, for the value of x equaling 1500, the z-score of that is going to be equal to 2.11. So what we're saying is that this value of 1500 in relation to the data is just a little more than 2 standard deviations above the mean. So this is going to be 2 standard deviations above where the mean is. Okay, so these are just 2 examples of how we can calculate z-scores given a set of data. Now, usually they're not going to expect you to kind of figure out what the sample mean and the sample standard deviation are. That data is usually going to be provided. But I figure since we're using this set of data, I figure we just kind of keep working with it. Okay. All right. All right. So let's take a look at another problem here. Here we want to take a look at how we can find the percentile of data values, and that's going to go back to a definition we have from the previous notes here. Let me see if I find that. There we go. So this is a calculation of position. So this is on page 2 of the notes we did before. So let's say, for example, maybe what I want to do for this data up here is I want to find p sub 20. And by finding p sub 20, what can I gather from this? Okay, this is the 20th percentile. All right. And k is what's equal to 20. That's what k is down here. So we write this as p sub k. So we write p sub 20. I'm looking for what data value represents the 20th percentile. So for example, for someone that scores like 39, that's like the first percentile, like it's the lowest percentile you could be, because no one's lower than the 39. Okay, but we want to find what score corresponds to the 20th percentile. Okay, so or whatever these are, I will just say that they're scores. So we'll call these and figure out which of these data value represents the 20th percentile. So what does the formula read for this? Okay, it says that it's the number of values less than hold on, guys, one second, please. Hang on. Okay, folks, I'm back. I realized I was doing something wrong, but I couldn't quite put it together, and I didn't want to like hem and haw until I had it figured out. But yes, I made a silly mistake here. So the process I actually began was just to convert a percentile to a data value. So if I want to find the data value that corresponds with the 20th percentile, because that's what I'm looking for here. I'm gonna look for something which is called an L. That's a locator number. So I want to find the locator number. The formula to do this is L is equal to K um, divided by 100 times N. So what I'm going to do now is I'm going to take that 20 and I'm going to divide that by 100. The N is how many values I have here, which in this case is 25. Because if I count the total amount of numbers I have here, that's going to be 25 numbers. So to figure out my L, that's going to be equal to 20 divided by 100. Not 1,000, just 100. Times 25. So 200 20 divided by 100. That's going to equal 0.2. 0.2 times 25. Just want to make sure, hang on. 25 times 2. That's going to equal 5. Now, if you get a decimal on this one, round up. In this case, we don't get a decimal, so the locator number is going to be 5. So what I'm going to do to find out what number corresponds to the 25th percentile or 20th percentile, I'm going to count 1, 2. This is in order now. 1, 2, 3, 4, 5. Okay, so this is where L is equal to 5. So basically what I'm saying is for this particular set of data, the 20th percentile is going to equal 55. So if you've got a score of 55 in this test, your score would be at the 20th percentile, meaning that your score would be like higher than 20% of the rest of the population. So that's how we convert from percentile to a data value. Okay. My apologies for the mistake before. I crisscrossed the processes when I was looking at this. So that's how we convert a percentile to a data value. We will look at more examples of this when we go into my method. All right, another one here, how we find a percentile of a data value. So let's say, for example, I'm looking at the value of 350. Okay, and I want to find out what percentile of that. So 350 is like piece of what K? What's the percentile here? Well, here's the value of 350. Okay, so and according to the formula I have here, finding the percentile of that value of X, where in this case, like X would equal 350, I want to find the percentile of this number. So what is that going to be? That's going to be equal to the number of values less than X divided by the total number of values. So if I want to find that, that's going to equal the total number of values less than X. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's going to equal 16 divided by 25 times 100. So if I take 16 divided by 25, that's going to equal 0.64 times 100. So that's going to be the 64th percentile. So we could say here that 350 is equal piece of 64. For that set of data, 350 corresponds to the 64th percentile. And that's how we find percentiles of data values. So we start with the data value, find its percentile. Down below here, we say what percentile we want to look for, and then we figure out what value corresponds to that percentile. I'm sure there'll be other examples in the videos that are available to you online for this as well. For this last set of examples here, we're going to go ahead and use StatCrunch. And I think StatCrunch is actually going to do this. So I don't know if I'm going to show how to find the outliers for this, because finding outliers is a complicated process. So what I'm going to do is I'm going to go and go back to StatCrunch here for this last question. And let's see how we do this here. So one thing we do have for this, we have the 5-number summary from our previous work. What constitutes the 5-number summary is going to be the min, the max, the median, because remember the median, that's Q2, We also have Q1 and Q3. I think though, when we do this, we're going to be able to get this from this anyway, from the box plot anyway. But I want to show you that at least we found this data already. We also have the interquartile range. So that's a question that's asked. You can get it from the summary as well by just running the measure center variation and position calculations we just did. Well, let's go and take a look at this feature, how we do this in StatCrunch. All right, so I'm going to run a box plot for this. I'm going to go to graph. I'm going to go to box plot. So go to graph, box plot. And on a graph, I'm going to graph the information that's, let me see if I can show that. No, I can't. See, reduce this a little bit. Yeah. Okay. So that's the information I want to do the box plot for. So I'm going to choose the data. Okay. I'm also going to go ahead and choose use fences to identify outliers and then draw boxes horizontally. So we're going to be able to use StatCrunch to find the outliers without having to do all the calculations involved to do that. Easier, I think, to do the boxes horizontally. Let's go ahead and press compute. Okay. So you see here, if we didn't have these two values, yeah, see 1500, that's definitely an outlier. And you remember that when we did the standard deviation of that, we found the standard deviation of that to be more than 2 standard deviations for that value. So that's an outlier. This is also an outlier. We take a look at this. We see, oh, we take a look at this here. It gives us some information here. It tells us we have 2 values. We have 25 values, 2 outliers. The IQR is 375. The lower limit gives us the 5-number summary right there. This particular value here, it gives us the upper limit, not the maximum. The maximum is 500. Now the maximum value of the data we know is 2500. But in terms of what comprises the box plot, the upper limit is 500 because 500 is the last number that is within normal range of most of the data. So these would be considered outliers here. Let's see what this looks like if we take out those 2 outliers and just kind of see what kind of data we have. So let's just take that out. And then let's go ahead and do a box plot today. And you'll notice here, what do we have when we go to these 6? You might just see a little more information. So you see it's going to tell you the number of values is 23 because we took those 2 away. The lower limit is 39, the upper limit is 500. It'll kind of repeat that same information here. And what a box plot does, it kind of shows you the dispersion of the data. If you take a look, like a quarter of the data is between here and here, between the whisker and Q1. Here's Q1. Quarter of the data is between Q1 and Q3. A quarter of the data is between Q3 and Q2. Q2, the median, and Q3. Let me start with that again. Here's Q1 and here's Q2. So a quarter of the information is between Q1 and Q2. A quarter of the information is between Q2 and Q3. And then a quarter of the information is between Q3 and the highest value here. So you'll see here, it's like really compressed. Like there's a lot of data that's lower. Here, a fair amount of the data is kind of compressed here. But between Q2 and then Q3, data is very spread out, much more so. In fact, it's more spread out from here to here than it is even between like 3rd quartile and the maximum. So this is what a box and whisker plot looks like. And this is how you construct it in the StatCrunch. And you can even use that to find outliers, which is very nice. So I hope you take advantage of these tools. Please look at the video before coming to class. And I hope you find this to be helpful. Thanks.